Okay, in this video we want to look at some of the theoretical ways of looking at the inverse of a matrix. So you might ask, how would a sixth grader approach a problem like 2x equals 5? And if you think about it, you'd multiply both sides of the equation by 1/2. And so you get 1/2 times 2x equals 1/2 times 5. And then since the 1/2 and the 2 equals 1, you get x equals 5/2. And 1/2 is the multiplicative inverse for 2. And the product of the two numbers gives a multiplicative identity, which is 1 for the sixth grade example. So for the steroid-induced system of equations, ax equals b, now we have more equations and more unknowns. Is there a concept of inverse for a? That's one question we might ask. Does a multiplicative identity exist? And finally, could we develop a sixth grade method for solving ax equals b using the same kind of idea? The good news, the answer to all those questions is yes. So let's start by defining some terms. A multiplicative identity for matrices is called the identity matrix and is denoted by an I. Each column of I has a 0 in every entry with the exception of a 1 on the diagonal. So if you see an identity matrix, first of all, they're all square, and I didn't mention that before. So you'd have an n by n identity matrix, and down its diagonal entries would only be 1s. All of the off diagonal entries, so anything that's not on the diagonal, would be 0s. The jth column of the identity matrix I is referred to as E sub j. So if we're talking about the jth column, we refer to that as E sub j. So here's the structure of an identity matrix. As I mentioned before, you have 1s down the diagonal. That's where the row index is the same as a column index. And then you have 0s in all the other entries. And then, of course, E sub j is the jth column of the n by n identity matrix. And so in its jth entry, it would have a 1. And just notice that we represent the identity matrix here as I with a subscript n. That just means that it's an n by n identity matrix. So the inverse of an n by n matrix A will be denoted by a to the minus 1 is what it looks like, and we read that as A inverse. A inverse. And you can probably see some similarities to the sixth grade problem, because if we had such a thing as matrix division, then a to the minus 1 would of course be 1 over a. So the notation fits. But when we see that a to the minus 1, we're going to refer to that as the inverse of the n by n matrix A. And so, well, if that existed and we had this system of equations ax equals b, we could certainly multiply both sides of the equation by A inverse. Of course, we have to remember that matrix multiplication is not commutative, so if we multiply on the left of A, on the left-hand side of the equation by A inverse, then we have to multiply b on the left-hand side. And of course, A inverse times A will equal to the identity matrix. And so we'd have the identity matrix times x is equal to A inverse b. And of course, the beautiful thing about the identity matrix is it is the multiplicative identity for matrices. And so we get x is equal to A inverse b. So this implies that if A inverse exists, then the solution to ax equals b is unique. And not only is it unique, but we know exactly what that solution should be. Namely, x should be equal to A inverse times b. So multiplying the right-hand side by the inverse will give you the unique solution to the system of equations ax equals b. So if an n by n matrix A has an inverse, we say that it is non-singular or invertible. Otherwise, A is said to be singular or non-invertible. So matrices, and we're talking about n by n matrices again, that have inverses are referred to as non-singular or invertible. If those matrices do not have inverses, then we say they're singular or non-invertible. So one of the questions you might ask, and we'll look at some theorems coming up, is how do you know when a matrix has an inverse? So just keep that in mind as we go forward. So now let's examine some important theorems related to the inverse of an n by n matrix. So the first theorem we're going to look at is if an n by n matrix A is invertible, then A inverse is invertible. And namely, the inverse of A inverse is A. So if A has an inverse A inverse, then A inverse must have an inverse as well, which is A. If A and B are invertible n by n matrices, then AB inverse, so the inverse of the products, is equal to B inverse times A inverse. And just carefully look at the order. If I take the inverse of a product of n by n matrices, then the inverse of that product is the second matrix inverse times the first matrix inverse. So their order has been changed. If an n by n matrix A is invertible, then A transpose is invertible, namely that the inverse of A transpose is equal to the transpose of A inverse. So this indicates that if we have the inverse of a matrix and we also have the inverse of its transpose, because the inverse of its transpose would just be the transpose of the inverse matrix. So let's look at a simple proof. We want to prove that for an n by n non-singular matrix A, the inverse is unique. Now this is important because that means that we know then that if we have the inverse of a matrix, there's only one. And so we don't have to worry about there being some other ways to multiply our matrix A by something to get the identity matrix. So we'll use a proof by contradiction technique. And so remember, proof by contradiction just means you make an assumption and then somewhere your reasoning leads you to a contradiction to your initial assumption, so the opposite has to be true. So as in all proofs, we write down what's given. So we're given A as a non-singular. A is non-singular and therefore has an inverse. And we need to write down what we must show, and in this case we must show that the inverse of the matrix A is unique. And so we're going to assume the opposite. This is our proof by contradiction step, and that is the inverse is not unique. So we're going to assume that the inverse of our matrix A is not unique. So if that's the case, then we can assume there exists two inverses, call one B and the other C, such that the identity matrix will be equal to A times B, which is B times A, and that would also be equal to A times C, which is C times A, because we've assumed that both B and C are inverses of A, and if we have the inverse of an n by n matrix, they do commute, so AB equals BA and AC equals CA. So it must be the case that B is equal to B times I, because anything times the identity matrix gives itself back. That's true. And then the identity matrix is equal to A times C because C is the inverse of A. So that means that BI is now equal to B times the quantity A times C. We can rearrange, and so that's equal to B times A times C. But B times A is equal to the identity matrix, so that's equal to the identity matrix times C. And of course, the identity matrix times C is C. So since B is equal to C, our initial assumption that there were two inverses for A is contradicted. And this implies that the inverse must then be unique. And it is the case that B is equal to C, and so we will just refer to that as A inverse. So we've shown that if you have an n by n matrix A, and this matrix has an inverse, then that inverse must then be unique. Let's consider an n by n matrix A is invertible only if it is row equivalent to the identity. So here's another theorem which says that A is invertible only if it's row equivalent to the identity. So recall that row equivalent simply means that A can be changed into the identity via some series of elementary row operations. So let's look at an example. Let's show that the matrix A is invertible if A is equal to minus 1, 1, 1, 2. So as our first elementary row operation, we'll combine rows 1 and row 2, and that will become the new row 2, giving us minus 1, 1 as the first row and 0, 3 as the second row. Our second elementary row operation will divide the first row by minus 1 and divide the second row by 3, giving us 1 minus 1, 0, 1. And then as our last elementary row operation, we will take rows 2 and row 1, combine them, and that will give us a new row 1. And if we do that, we see that now our matrix has been changed into 1, 0, 0, 1, which is the identity matrix for our 2 by 2 matrices, I should say. And so from our theorem, if A is row equivalent to the identity matrix, then this indicates that that matrix A, minus 1, 1, 1, 2, is also has an inverse. In our next video, we will actually start to look at how you can find the inverse of a matrix if it exists.